So at this point, you completed your freezing point depression mini lab, and hopefully what you saw for this portion is that the beaker with the ice and the salt got way, way colder, like probably, I'm hoping that all of you clocked in at less than 0. So let's talk a little bit about what was going on. The main idea behind today's lecture is going to be something called freezing point depression. So freezing point depression is simply a drop in the freezing point. Oops, point. Nope. Gotta get my pen back. It's a drop in the freezing point of a solution. So whereas before we said water freezed at 0 degrees Celsius, well, if you add salt to water, then it might freeze at some point less than 0. Scientists don't know entirely why this is, but the kind of overarching theory that we currently have is that this is due to, and here's going to be a vocabulary blast from your past, the solute particles disrupting the ability of the solvent, and we'll talk about all these words again in a second, to form a solid. So a drop in the freezing point of a solution, so lower than normal freezing temperatures. It's due to the solute particles disrupting the ability of the solvent to form a solid. So let's review. Solute, remember that is a solid dissolving into a solvent. So the solute is the thing that you mix in, and the solvent is the thing doing the dissolving. Almost every situation that we're going to look at, the solvent will be water. So here's kind of how this works, is that in order for water has this kind of little bent structure. It looks kind of like a letter V. In order for water to freeze, the water molecules have to line themselves up in this very, very beautiful, very deliberate crystal-like structure. Now the problem is, if you mix something in with that water, it's going to disrupt the ability of this pretty structure to happen. So if you stick in some big sodium chloride, sodium ions, what you'll have is the inability for this crystal to form. We won't see it happen, and what that means is that the freezing point then will be lower than pure water. So there are two ideas that we need to look at in order to figure out the math behind why this works. The first concept that I want to introduce you to is something called molality. And molality, when I first heard it, I thought my professor was saying something wrong. I was like, no, there's no such thing as molality. There's molarity. There is also molality. So molality, some of this might look a little familiar. Molality is the moles of solute divided by the kilograms of solvent. So moles of solute over kilograms of solvent. So I want you to practice. We're going to do 2 practice problems with this, and then that will lead us into actually getting back to freezing point depression. So bear with me as we take this short detour. So it says calculate the molality when 75 grams of magnesium chloride is dissolved in 500 grams of solvent. Okay, quick review here. Remember that with the periodic table, imagine that's your periodic table, the patterning for how to figure out what the formula of something is. You're going to get into trouble if you see magnesium chloride and just assume that it's MgCl. That won't always be the case. So let's review. Remember this, the pattern of charges. We start with +1 and +2. We skip the transition metals, then we go to +3, ±4, and then down to -3, -2, -1, and 0. Hopefully this rings a bell, at least distantly. We're going to have to revisit that. So get a periodic table in front of your face, either by finding one on the desk or by opening one in another tab. So if you find magnesium chloride, magnesium is a alkaline earth metal, which means it's going to have a +2 charge. Chlorine is a halogen, which means it's going to have a -1. So remember, when we bring these two things together, our charges will crisscross, and we will be left with MgCl2. This is going to end up being very important for a variety of ways that you remember how to do this. So my expectation from here on out is that you remember to check the periodic table, do your crisscrossing, and make sure that you have the right ionic formula. Okay, so let's go back to the question, molality. The first thing we need is moles of solute. Well, our solute is magnesium chloride, so we have 75.0 grams of magnesium chloride. We need to do a T-chart conversion to get us into moles. So I'm going to have 1 mole up here. And in order to find the molar mass, I'm going to look on my periodic table. I need 1 magnesium, which clocks in at 24.31, plus 2 chlorines, each at 35.45, gives me a molar mass of 95.21 grams. So again, I'm going to do 75 divided by 95.21, and I get for just my moles is 0.788 moles. I can keep 3 sig figs. I'm not done yet, though, because the second part is kilograms of solvent. One thing to remember is that there are 1,000 grams in 1 kilogram. So be prepared to go back and forth between those. 500 grams, then, will be equal to 0.5 kilograms. So let's see, I'm going to have 0.788 moles over 0.5000 kilograms. Kilograms. So that will give me, 0.788 divided by 0.5, a molality, I can keep 3 sig figs, of 1.58. Now the unit that goes with molality is going to be a lowercase m. Molarity was a big M, molality is a little m. Okay, let's keep going. Let's try one more. 100 grams of sucrose is dissolved in 1.50 liters of water. What is the molality? Okay, so again, we're in grams, so I need to do a little converting. Look at that nice teacher who gave you the molar mass of sucrose, so you didn't have to figure it out. Equals 1 mole. So we are going to do 100 divided by 342.3, and that will give us, looks like we can keep 4 sig figs this time, 0.2921 moles. Now, if you'll see here, our solvent is 1.5 liters of water. So when we are working with water, there's a couple useful things. 1 gram of water, if you remember from the density, 1 gram of water equals 1 milliliter of water. What that conversion also means is that 1 kilogram of water is equal to 1 liter of water. So we really like working in liters because all we have to do is take the L off and put on a kg. 1.5. 1.5. Oh, hang on. Got to get my pen back. 1.50 kilograms. Okay, so let's take a look and see what that will be. So 0.2921 divided by 1.5. And again, it looks like I can keep 3 significant figures, which will leave me with 0.195 molality. Again, it's that lowercase m. So why do we have to even worry about molality in the first place? The next page is going to tie together freezing point depression and molality. So let's go take a look at that. So how to determine freezing point depression? Let's connect these two ideas. We can actually calculate by how much our freezing point will be depressed. Now when I say depressed, again, that's another way of saying I want to know by how much my freezing point will drop. So let's take a look at the formula that I have here. We're going to call this delta T sub F. This is, delta, remember, is change. This will give me the change in the temperature of my freezing point, is how you can kind of refer to this unit. This will always be a drop. So whatever you see, it will decrease rather than increase. We're never going to be adding this number to anything. So in order to find delta T sub F, it's 3 different units added together, or multiplied together, excuse me. The first one is the molality of the solution, right? So there's that number. I know we needed that for something. The second part of this formula, we're going to multiply it by a constant called K sub F. This is a constant that is unique for every solvent. A constant that is unique for every solvent. Most often I will be giving this constant to you in a problem, so it's nothing that you'd ever have to look up. The third thing that you need is, that's a lowercase I. Now, what is this? This is, I stands for the number of ions Okay, got to go get my pen back one more time. I'm sure there's a quicker way to do it. I just don't know what it is. The number of ions formed in solution. So let's do a quick review here. The number of ions formed in solution, I should say, by the solute. Here's what I mean by that. Let's do a quick little review. Ionic versus covalent. So remember that ionic is between a metal and a nonmetal. Covalent is between two nonmetals. My expectation is that you'll be able to recognize if a formula is ionic or covalent. So here's why this matters. If you drop a covalent compound into water, it does not ionize, which kind of makes sense. If it was ionizing, it would be an ionic compound. If it doesn't ionize, that means that I equals 1. Sugar is a great example. It's a covalent compound. You drop it into water, and it just stays all together in one sugar molecule. Ionic compounds, on the other hand, break apart into ions. So some examples of this. If we looked back over here, we looked at magnesium chloride, if you remember. Magnesium chloride. When we're thinking about magnesium chloride ionizing, we can say that I, oh good grief, equals 3. Pretend that still says magnesium chloride. Here's why I equals 3. We have MgCl2. I equals 3 because every magnesium chloride that we drop into water, we get 1 magnesium and 2 chlorines. So we kind of get 3 pieces that make up 1 magnesium chloride. Let's look at another one while we're still thinking about this. Let's look at sodium chloride. It's here in this first problem. Now if I look on my table, sodium is +1, chlorine is -1. Together they make NaCl2. Well, for NaCl2, I equals 2. We get 2 ions every time we drop sodium chloride into water. We get a sodium ion and a chlorine ion. Okay, so let's bring it back up here to this whole equation. To find how much our freezing point drops, we look at the molality of the solution, this K sub F, which is going to be a constant, unique for every solvent, and then I is the number of ions formed in solution by the solute. Okay, so let's apply this here to problem 8. The easiest way to see it is to just dive in. So delta T sub F equals, let's look here. What would be, that should say, the freezing temperature of a 0.029 molality sodium chloride solution? And if you look here, I give you K sub F is equaling 1.86 degrees Celsius per molality. So let's take a look here. I give you the molality, 0.029 m. I also give you K sub F, right? That's the next part of our equation, 1.86 degrees Celsius per molality. The last thing that I need is this I. Now we said earlier, we figured out sodium chloride. It's going to be a 2. Now this is a unitless number. We just get to write 2. Now if you're keeping track of your units, our molalities cancel out. And so we are going to figure out what our delta T is going to be by multiplying 0.029 by 1.86 by 2. And now I get an answer of 0.10788. I can keep 2 significant figures according to that number. So 0.11 is going to be my change in temperature. And again, this will be a drop. So, for example, if we're talking about pure water that freezes at 0 degrees Celsius, now it might be freezing at negative 0.11 degrees Celsius. So what I'd like you to do is do the remaining 2 problems and then go on to the freezing point depression practice problems in Schoology.